Now we have to solve a system of differential equations where we have two functions of t, x and y, and there are two equations and both of them are entirely functions of x and y and they are linear, as you can notice. So let's do this. Let's just go ahead and rewrite them. So we got x prime equals negative 2x minus y, and then we got y prime equals 4x plus 3y. And if we want, we can rewrite this as in a matrix form as shown below. So what we have is that we have this column vector x prime y prime written as a 2 by 2 matrix times this column vector x and y, where what we are going to do is we are going to try to solve for x and y as functions of t, and the derivatives are functions of x and y entirely. So the situation is kind of easy here. So if you recall, our procedure is this, that we look at the eigenvalues of this coefficient matrix, okay? And then we shall find the eigenvectors and then we would be able to write the solutions, okay? So you know this, if lambda is an eigenvalue, all right, is an eigenvalue of this matrix, okay, then how do we get our lambda? We get our lambda by the following technique, that is, we will go ahead and just subtract lambda from the diagonal elements, all right, and set the determinant equal to 0, and the solutions are going to take us to the eigenvalues. So what we get here is negative 2 minus lambda, right? Minus lambda, and then we have, I can just do this, that is, just copy and paste it, right? And so here we multiplied these diagonal elements, and then we shall multiply the elements in the other diagonal and subtract it, right? So doing that, we got negative 1. I mean, I could have written negative 1 before, but multiplication is commutative, so it doesn't really matter, right? So if I FOIL this one, what would I get? You can see we will get, what we will get is negative 6, negative 2 times 3, and then we will have negative 6 lambda and then minus 3 lambda. So that will give us negative 5 lambda, right? Okay. And then negative lambda times negative lambda will give us a lambda square. Okay. So we got a lambda square here, and this whole thing becomes what? Plus 4, right? So what we have again is lambda square minus 5 lambda minus 6 plus 4, and then we have, after the cancellations, we got lambda square minus 5 lambda minus 2 equals 0. Now this is the time to stop and check our calculations. So we have, oh, by the way, this would negative 2 minus lambda would be plus 2 lambda. So, and that is negative 3. So you can see I made a mistake. I'm sorry about that. Okay. So what does this give is that the factors will be lambda minus 2 and lambda plus 2. So lambda is going to be, lambda minus 2 and then lambda plus 1. So the eigenvalues are -1 and 2. So we have two distinct eigenvalues here. So now we are going to do what? We are going to find the eigenvectors corresponding to this, and that will give us the solutions according to the algorithm that we saw in our notes. Okay. And now recall the procedure that if we have uv, okay, an eigenvector of lambda, okay, uv is an eigenvector of lambda. What does that give us? That gives us that we should have, and actually let me put this in, just in a appropriate format. So that will mean what? That is going to simply mean that this product of these two matrices involving u and v, that has to equal what? 0, 0, right? So that was the procedure that we used to find the eigenvectors for a given eigenvalue. So let's just go ahead and find it for eigenvalue -1. Okay, so if we do that, what do we find is that we find that here we are substituting simply how much? -1, and then we shall substitute the same value over here, -1, and what is that going to give us for the system of equations is that this becomes -1 and this becomes how much? 4, right? So what happens? We will see that both of them imply the same equation. Actually, if you multiply them, what will happen is the first one will give you -u minus v equals 0, and the second one is going to give you 4u plus 4v equals 0, and each one of them amounts to what? Simply that u equals -v, right? So if we have I'm sorry. Okay, so if we have a relationship like this, then for any eigenvector, we have what relationship we have? We got the relationship that uv is an eigenvector if u equals -v. So we can rewrite this as, if we want, as -v and then v. And this just shows us what? That all the eigenvectors corresponding to -1 are multiples of this vector -1, 1, right? And likewise, let's just go ahead and find the eigenvectors rather, that correspond to the other eigenvalue, that is 2. So here we will have -2 minus 2, and here we will have 3 minus 2, the same thing, equals 0, 0. So what does that give us? That gives us the following, that is we get, should go carefully, -4 here and 1 here. So just like before, remember this, that is, I hope I'm not causing any confusion by just overwriting over there. This is -4 minus, see, -4 times u minus 1 times v, that equals 0, then 4u plus v equals 0. So either of them tell us how much? That v equals how much? negative 4u. That means for the eigenvalue 2, right? What will happen is that this will look like, this time let's write them in terms of u. I mean, we could write them in terms of v, and we will have very similar result, sorry, u here, but uh, if we want to avoid dealing with fractions, then this might be a better strategy. Okay, so here we go. So all the eigen vectors of lambda equals 2, okay, they are all multiples of who? 1, negative 4, right? And if we go to lambda equals negative 1, okay, then if you recall, let's just quickly recall, where is that? Right here, that all the eigenvectors are multiples of how much? Negative 1, 1, right? Okay, so when this happens, then our solution, or our solution for xt, yt, that is going to look like, so here is xt, then yt, all right, that is going to look like a constant, the general solution, I mean, you'll take c1 as a constant, then e to the power, just take one of the eigenvalues times t, and then times this eigenvector, right? And then for the other one, you will simply get c2, or let me just make a change within these. So we got what we got here. We got c2, and then negative 1 times t is negative t, and then we got negative 1, 1, or 1 negative 1 would have been fine as well, because it is a direct multiple. So what happens here? If you multiply them out, I mean, here we have the solution written, but if you want, you can multiply them out, and a set of general solutions will be what? C1 times e to the negative t first, and then minus C2 times e to the negative t. That's what we get for xt. And what do we get for yt? We get negative 4 times c1, just multiplying component wise, and then plus simply this quantity, right? So what we have at the end finally is this, that our xt is, okay, our xt is this function of t, right? And our y value is a function of t over here. And if you want, you can, often be able to eliminate this t between the two and get a direct relationship between x and y, and plot the relationship between x and y for for different values of c1s and c2s, and that is called a phase plane that I'm going to show you graphically through an easy app. All right, so what we had was that to begin with, we had this system of equations, right here, and then we got this set of equations as the general solution. Okay, so now let's just go ahead and look at, remember this, for this system we can plot a slope field or direction field. Okay, so let's go ahead and do that using that online software that we are using. Okay, So remember, we are using, in addition to MATLAB, that's slope field plotter, and we are using it from Bluffton University. Okay, so here is the, here is the plotter that is created by Dr. Darrell Nestor. So let's just go ahead and put the values in here, right? And what we had here is, I forgot so fast, 4x plus 3y. Let me make sure quickly. Yeah, 4x 3y is plus 3y is good. Okay, so we got, let's just plot with the same way. So here is a slope field or direction field, or say vector field. We'll say that in different scenarios, okay, of this system of equations. And if we want to see the phase plot, so let us go back to our calculations. So these are the XY solutions for, for the parameters C1 and C2. So say we took C1 equals 0 and C2 equals say 1, very convenient values. Okay, then what they will change to is that they are going to change to x equals e to the negative t and y equals e to the, sorry, negative e to the negative t and y equals how much? Just e to the positive t, right? So what happens? All these points will lie on the line y equals negative x. And notice this, that here e to the negative t, as t becomes larger, e to the negative t will become smaller. So the arrows will approach towards zero, or the solutions will approach towards zero as t increases. So what we would do is that when we go back to our plot, we will we will ask for the values corresponding to say these 2 points as initial values, say 3, negative 3, and because if x is 3, y is negative 3, and vice versa. If x is negative 3, y is positive 3. Or let's just go ahead and look at that. So let me just bring the plot back for you. Okay, so here we are. Say, let's look at the, the xy graph, or a graph between x and y. If we take 3, negative 3 as the initial point, so you can see here is this straight line approaching towards origin, and there they are, one is going according to e to the negative t, the other one is going according to e to the positive t, all right, or and then if you look at the, say we just change these, they go from negative 3 to 3, then it will come other way around right here. All right, and then let's look at the other situation. Now, before we go to the other situation, let me fix a slip of tongue that I just had. That is, one of them goes according to e to the negative t, and the other one not as e to the t, but negative e to the negative t. So it will go on the other side. All right. Yeah, now let's go back to the other straight line solution. That is, now we are going to take this system, and now we will, let's change C1 to 1 and C2 to 0. Okay, and so then what will happen? Our x will be simply e to the 2t, All right, and y is going to be negative 4 e to the 2t. So in this case, what we shall have is that what is y? Y is negative 4 times x, right? Okay, so that's the line that will give us the solution. X is e to the 2t and y is negative 4e to the 2t. So when we give initial conditions, let's go for small values of x and y, all right, because you can see, depending on the value of t, these will become very large. So let's choose, say, I mean, we can just try, we don't have to do any calculations. Okay, so say we take x as negative 0.03, y would be, sorry, x as 0.03, y would be negative 0.02, and we can switch the signs if we want, so they will change. So let's go back to our graph and look at this straight line there. So this time we decided to take x as 0.03, so y will be negative 0.12. We took these values so that we can stay within our window of negative 4 to 4, negative 4 to 4. So you can see here that that line changed, and let's just, for symmetry, go to the other quadrant. Okay, so here is the other straight line solution. So what we got here is that we got this straight line solution, y equals negative x, and this one is y equals negative 4x. Okay, and then and you can see in this case the points are moving away from the origin. Why? Because you can see x and y, they are directly related to the positive powers on t. So here we are just going away from the origin. And let's discuss something later. That is, if you look at the phase plane, like look at the straight line solutions according to the around the two lines, here is what you get. And for these guys, you have these here. And what you shall see is this, that when we have this type of a situation, I mean, you can go ahead and make a lot of, you know, lot of curves here, okay, and their x and y traces will come out here automatically, okay, and we will, in some courses, we are doing this via MATLAB as well. So anyways, so, and in this case, 0, 0, the point here, we'll call it a saddle point. All right, because it's neither source nor sink. So what I meant by source or sink, because if you look at this thing, the line y equals x, along that you can see all the arrows are approaching towards 0. While if we look at the other line, which I have lost in this right here, y equals negative 4x, here they are moving away from the origin. So we neither have a source nor have a sink, and I'm going to elaborate that more in the next example. All right. So now let's take this system of differential equations. All we have different is this coefficient matrix. So say we go along the same lines as we did before in the last question. What we shall find is that the eigenvalues are 1 and 3. They are different and they have the same sign. And an eigenvector corresponding to one of them is negative 1, 1. The other one is 1, 1. So the general solution is going to be of which type? And so this is, we'll just take C sub 1, right? E to the t corresponding to lambda equals 1, right? And you can see that all the multiples of this vector are the eigenvectors, and then we shall do the same thing. And at this time, uh, we are changing the constant, and the power on this would be e to the 3, sorry about that, e to the 3t, and this will be 1, 1, right? So if you take C1 equals 1, C2 equals 0, then you can see y equals negative x will be, the solutions will lie on y equals negative x. And on the other hand, if you take C1 as 0 and C2 as 1, they will go along y equals x. So let's go ahead and plot our solution in that plotter and see how they look like, right? So what did we have is we had 2x plus y, and then we had x plus 2y, right? Okay, so we got the solution. Then you can see here is our line y equals negative x, and here is y equals x, and we can realize them. Let's just do 0.01, say 0.01, submit. So this is this line, and now of course it's moving away from the origin, right? Okay, and here the x and y graphs are identical here, all right? And if we do negative 0.01, and we are taking small values because they're going in the positive powers of E, and we want everything to fit within this window, okay? So here is the other side, all right? And now we will do this. Let's change it according to the other values. So here is y equals negative x, okay? And there we are. So here are the straight line solutions, and in this case, we are moving away from the origin on both the sides. All right, and then if you look at the solution curves, you can see that everything is emerging out of the origin. All right. So what happens here? We are just moving away from the origin when the eigenvalues were distinct, and we had and they are both positive. Okay, so in this case we call origin a source. All right, and let's just take up a case in which we have this, that is, we got the eigenvalues are different, but they have opposite signs. Okay, so now we are just looking at a slightly different case in which the eigenvalues are different and they don't have opposite signs, because that was our first example. They are both negative. So if we go with the same routine in finding the eigenvalues and eigenvectors of this matrix, what we shall find is this, that both the eigenvalues are negative, right? And when we look at the general solution, what we have is, I brought it from the previous one. All that changes is this changes to -1. Now the eigenvectors correspond to this, and this changes to -3t, and the eigenvectors correspond to this. So here eigenvalues -1, so we got e to the -1 times t times, this is a basis element of the eigenspace, or you just say all the eigenvalues are multiples of this, and here the eigenvalue is -3, so we got e to the -3, and we got this eigenvector. So now again what we will have is x equals y and y equals -x. They will be our straight line solutions. And the difference in this case would be this, that earlier, remember when these were positive, all the arrows were emerging out. So here, let's see what happens. Now here still we have our earlier plot where you can see y equals x and x equals negative y in both the along both the lines. We are going away from the origin. Now if we change according to our new system, that is both our eigenvalues are negative. Now you can see that along both the lines they are approaching towards the origin. So say we give initial condition as 0.03, negative 0.03, we get this line, and if we just change the quadrant, okay, then you simply get this line. If we keep them the same, we will be in the first quadrant, and here if we are still keeping them the same, we are in the in this quadrant. So now we have along both the lines, we have these solutions approaching towards 0 0, right? Okay, so if you look at all the if you look at the phase plane here, you can see these solutions are approaching 0 0. So we'll call 0 0 in this case what? A sink, right? Remember when both the values were positive, it became a source. Now we have a sink at 0 0. All right. Now we shall discuss in the next video. This video has had enough. Okay. The case in which we have both the eigenvalues equal. Okay.